and welcome to this lecture. So, in this lecture we are going to start looking at sequence spaces, function spaces which were introduced in the previous lecture, and specifically we will try to define inner products and norms in these spaces. Okay. So, it turns out inner product for infinite length sequences are connected to convergence also. Okay. So, to see that, let us see. We have the usual inner product in finite dimension, right? If you have a vector, two vectors in finite dimension, you know how to define inner product. Even in complex, you know how to do that, right? So, let us think about how to extend that definition to infinite dimensions. Okay. So, here is a very obvious and simple extension for the real case. Let us say you have two sequences x1 to xn going on forever. Y is another sequence y1, y2, yn going on forever, and xi and yi are real in this case. So, if it was stopping at n, I know how to do inner product, right? Just multiply and add. There is no problem there. I am going to get a real number and I am happy with that inner product, right? Inner product has to take two vectors to a real number. Now, when you have an infinite sequence, there is just one little problem here. When you do the inner product x comma y in the same way and extend, you can't stop at x and yn, you will have to do a plus dot dot dot. So, it keeps on going forever, right? It becomes what is called an infinite series. So, the inner product becomes an infinite series. Once again, you can recall from your math 1, we studied infinite series a lot in math 1. We saw how sometimes the infinite series converges to one value, and we think of the series as being equal to that value, right? What happens there? And sometimes the infinite series diverges, it does not converge, all sorts of problems like that are there. So, while we define these sequences, or while we think of these sequences as vectors, we have to be slightly careful when you think of the inner product. The inner product can diverge off to infinity, right? So, if you extend the normal definition. So, what we really need is these inner products, for them to be properly well defined and not deal with these kind of divergent problems, right? If diverges to infinity, at least it's okay, you can say infinity, but there are these infinite series which may oscillate and all, right? So, you may get into trouble there, okay? So, which may not converge anywhere. So, then what do you do with these inner products, right? So, they are not defined for some vectors are not defined, it becomes complicated, right? So, this kind of series, it should converge for the inner product to be well defined. So, you see the difficulties with infinite dimension, right? So, the convergence issues start showing up. In the finite dimension case, I never had to worry about it. In this case, I have to start worrying about convergence issue, okay? That's one thing. So, even in complex, actually, so let us say these xi, yi are not real, they are complex, and let us say xi is ai plus jbi, yi is ci plus jdi, okay? So, these are two complex numbers, and of course, we can extend the inner product definition just like we did before, x1 y1 bar, x2 y2 bar, xn yn bar plus so on, okay? Now, if you do that, you see you will get something like this, okay? So, this is just a multiplication. So, the real part will become, you can see if you multiply these two, the real part is ai ci minus bi di, right? Or conjugation, okay? So, forget the conjugation. So, you have to conjugate this, so ci minus j di. So, when you multiply this, you will get ai ci plus bi di. So, that is the real part, as the real parts are getting added here, but they go off to infinity, okay? They do not stop here. And look, likewise, the imaginary part j times, once again, there is an infinite sequence. The real part is an infinite sequence, the imaginary part is an infinite sequence. Both of these parts have to converge for us to meaningfully define an inner product for these kind of cases. So, how do we deal with this convergence? It is a bit of a pain. I do not want to be worried about whether or not my inner product between two vectors are going to converge or not, right? So, there is one very nice way to get out of this issue, and that is the definition of a particular type of sequence space. All possible sequences we do not want to include, right? We want to include only those sequences which have some nice convergence properties, so that inner product of sequences can be very nicely defined, right? Things like that. So, our objective in this sequence definition is something like that, okay? So, when we want to do that, you can define something called an L2 sequence. So, this is a very famous sequence space, it is called L2. It has a certain type of infinite sequences. What are these types? This is the set of all sequences x1, x2, etc. xi, let us say, is in complex, it could be real also, generally we can think of complex, such that the real series mod x1 squared plus mod x2 squared plus so on, this infinite series for any sequence, this infinite series has to converge to a finite real number, okay? Only those sequences for which this infinite real series converges to a finite real number, I am going to include in my sequence space L2. Okay, so it's called L2, it's not L squared, it's defined, it's usually pronounced as L2, small L2 sequence space. So this L2 sequence space is a subset of all possible sequences. All possible sequences are not allowed in L2. In L2, only those sequences for which mod square of each of those values, if you add them all together and go off to infinity, that series should converge to a finite real number. Okay, it cannot diverge off, it cannot diverge, it cannot go off to infinity, it cannot keep oscillating or anything. It has to converge to a finite real number. In that case, I use that sequence, otherwise I add that sequence, include that sequence in L2, otherwise I don't do that. So here are a bunch of examples. So here are a couple of examples. You remember the geometric series 1a, a square, etc. This will belong to L2 if mod a is less than 1, right? So of course, if you have to square this, so it will get 1 plus a squared plus a power 4, so it will be 1 by 1 minus a squared. So if mod a is less than 1, this is going to converge, right? So that we know to converge to 1 by 1 minus a squared, right? So this converges. Here is another sequence 1, 1 by 2, 1 by 3, etc. This also is an L2, because if you do square, it becomes 1 plus 1 by 2 squared plus 1 by 3 squared, so on. So because of the squaring, this becomes convergence. So this as a sequence, if you make it into a series 1 plus 1 by 2 plus 1 by 3, so on, you might remember from math 1, that actually diverges, right? So it goes off to infinity. So it doesn't converge, but converge to a finite number. But if when you square it, see, this is L2 needs squaring, right? So it becomes 1 plus 1 by 2 square plus 1 by 3 square, etc. This is in L2. Now examples of sequences not in L2, if you have 1a squared with mod a greater than or equal to 1, this will not be in L2. If you add up, even if a is 1, 1, 1, 1, 1, 1 is not in L2. Okay, if you add it up, it blows off to infinity, right? So this is not in L2. Here is another sequence 1, 1 by root 2, 1 by root 3, etc. is not in L2. Why? Because when you square and add, you get the harmonic series 1 plus 1 by 2 plus 1 by 3 plus so on, and that diverges off to infinity, right? So it doesn't have a finite convergence. So these are some examples to show you that not all sequences are in L2, only some of them are. Okay. So it turns out you can define inner product and norm in L2 just by extension. Okay, so you have two vectors x and y in L2. Let's say these are in L2 now. Then you can define the inner product xy as x1 y1 bar plus x2 y2 bar, and then it turns out this actually converges. It's enough to enforce this L2 requirement on each of these vectors, and this converges. Okay, so we will not prove this result here. It involves a lot of technical details, and it's not interesting to us. But what's interesting is if you restrict the sequences based on some convergence, there's no problem with the inner product. It just goes through as before. Okay, so the inner product you can extend like this. Norm also you can extend like this. What is norm x squared? It's just inner product x comma x, and that is the same as this mod x1 square plus mod x2 square, which anyway has to converge to a real number, so obviously it will converge. Okay, so norm converges quite easily, and inner product also converges in this case. So if you want a hint of the proof, it involves something called Cauchy-Schwarz inequality, and then something called Cauchy sequences, and then you appeal to this convergence and absolute convergence, and that implies the convergence of the Cauchy sequence as well. It's a little bit involved, but anyway, that's technical. We are not interested in that. Okay, so basic point of this slide is if you restrict the infinite dimensional vector space to only some things which converge properly, then you have hope of defining inner product very nicely and proceeding further. Okay, so that's the idea. Okay, so what about for signal function spaces, right? So for us, sequence spaces are sort of interesting. We like them, but we are not studying them mainly here, right? So we are studying function spaces. We are studying signals. Signals are what is interesting to us. How do you define inner product between two signals like this? I'm restricting to the domain 0t. You can also go anywhere else, or you can not restrict. You can let it go infinite. That's not a big deal, but I'm just restricting to make it very clear and simple. So we've been thinking of this signal by sampling. We are thinking of this as sort of being represented by some sequence, and n is going to go to infinity, so this will go off to infinity. That's one way in which we are thinking about it. Of course, we can think of this whole thing as a vector itself. It's possible, but I'm trying to build up some intuition to get towards the inner product, right? So that's what I'm trying here. So you have y of t here, and y of t also you can sample down like this with n samples, and let n go to infinity, and you can sort of get a vector which maybe represents the signal closely. Okay. Now, if you think of these two guys, I know how to do inner product for this, right? So, maybe what I can do for the inner product between x and y, the x of t and y of t, is simply do this, okay, and then hope for some convergence here. But it turns out this is a bad idea, this does not work. Why? Because when n goes to infinity, right, so there are too many values here and then it just blows up in front of you, you can't do much with this, okay. So, you do not get a proper sort of convergence here and it does not work properly. What is much better is to do some sort of a Riemann sum. So, how do you do a Riemann sum? So, you divide by n, okay. So, you know that there is a sampling and holding going on, right, between 0 and 1 by n, I know that my value is going to be held at x of 0. So, I have to sort of multiply it by the length of that interval to get a Riemann sum, which I know will converge, okay. So, I mean for good functions x of t, y of t, you know, bounded functions, I know that the Riemann sum is going to converge and will get a good nice value, okay. So, this kind of an idea works, okay, when you tend n to infinity. Of course, you have to tend n to infinity. When you tend the Riemann sum with n to infinity, you can sort of define the inner product between x of t and y of t when they are complex. So, this is all illustration with real values. So, I did not do overline conjugate and all that. So, when they are complex, it looks like a very good motivation, you can look at this definition and then go towards an integral as the inner product between x of t and y of t. Okay, so, this is the Riemann sum is going to go towards this integral 0 to t x of t y of t bar dt. Okay. So, this will have a real part and an imaginary part. You integrate the real part and imaginary part separately, you will get the integration. So, this is a very sort of motivation to show you why the inner product between two functions x of t and y of t can involve an integration. Okay, and you can see how that is sort of motivated from the sequence picture. It is just motivation, this is not rigorous proof or anything, it is just to show you why some definition like this sort of makes sense. Okay, so, integral from 0 to t x of t y of t bar dt. Okay, summation replaced with integration when you go towards function spaces. So, this is a promising sort of idea for function spaces. So, this lets us define a new function space. So, of course, this integral has to exist, right, it cannot go off to infinity, this Riemann sum has to converge, the x of t, y of t have to be bounded and all of that has to happen. So, to ensure that that happens, we will now define a function space which is called capital L2 and then restricted to the domain AB, okay, any domain AB. I was doing 0t before, but you can do any AB, okay. So, here is the definition of this function space. This is a particular function space, not all functions are included here, only those that behave properly so that my integration will work properly, okay. So, the set of all functions x of t from a comma b to complex such that this integral, what is this integral? Integral a to b mod x of t squared dt is a finite real number. This guy is defined to be this L2 AB. So, all functions from the interval AB to C that are absolutely integrable in some sense, right, integral absolute square integrable, okay. So, integral a to b mod x of t square dt has to be finite, okay. So, a lot of functions that will satisfy this. Here are some examples. You can do x of t equals t, x of t is sine 2 pi k t by t in 0 to t in any interval a b. You can also do you can do any kind of function as long as the interval is finite and it's bounded, you know that the integral will exist. All these kind of things you can do, many functions that you can think of and draw, many signals that you use in electronic systems will be in L2. Only if you let the signals go off to infinity, right, like for instance sine omega t, right, if you go from 0 to infinity, for instance, sine omega t is not absolute square integrable. Okay, you can see if you integrate it and then sine omega t will sine square will become all positive, and then if you keep integrating it will go off to infinity, right. So, it will not be finite, okay. So, the sine omega t is not in L2. So, that is one example. I have not shown that example here, I do not know why. I hope, let me just reinforce that example for you. If you take sine omega t and then you let the domain be from t belonging to, let us say 0 infinity, okay, infinity. So, this does not belong to L2 of 0 infinity, okay. So, you can see that, right. So, if you do sine square omega t, sine omega t will look like this, right, it will look like this, it will go on and on forever. What will happen to sine squared? If you change the color, sine squared, I think it will go like this. So, it will go like this, okay. So this should be quite okay. I'm not drawing it very precisely, sort of like this, okay. So it will go on and on and on. So the integral will not be finite, okay. So that is something to worry about. So integral sine squared omega t from 0 to infinity dt is goes off to infinity, okay. So it diverges to infinity. So sine omega t is not there. I have shown you two examples of signals with only finite support. So if you make the domain infinite, then a lot of signals on sin omega t you use and all will not be in L2. But you know, if you do even finite, for instance -1 to 1, and if you think of a signal like 1 by t, it will not be in L2, right. So because it is 1 by t at 0, it goes off to infinity, and you do squared, you can't integrate, you won't get a finite value there, right. So that's a problem. Likewise, even L2 0 t, and if you do 1 by t minus t by 2, this will also not be in L2. So if you do this kind of crazy functions that go off to infinity, it will not be there. But typical functions that are bounded and the interval is also bounded, then they will be in L2. So most cases it will work out. Even sine, if you restrict to 0 to t, it will be in L2. There is no problem. If you restrict the domain to the 0 to t, it's okay. If you only when the domain goes out to infinity, there is a problem. So what we are doing here is not including all possible functions into a function space, but only those that are well behaved like this, that they don't blow up in some sense, they're well behaved. When you do that, you can define the inner product and norm using the integration idea that we had before. Let's say x of t is in L2, y of t is in L2 in interval a b, then the inner product x y can be defined as integral from a to b x of t y of t bar dt. Okay, so this is a very important definition to keep in mind. In function space, the inner product is integration, integral a to b x of t y of t bar, and of course norm x squared is in inner product x comma x integral a to b mod x of t squared dt. Okay, I want you to step back and think about all this a little bit more carefully. We were traditionally thinking in finite dimensions of vectors as being a vector of length n. You know how to define inner product, you know how to do norm. Now, when you have a signal itself and you are thinking of a signal from a to b as a vector, how do you do inner product? You have to do integration. You have to multiply, do the y of t bar and multiply and do integration. How do you think norm? How do you do norm? Norm is mod square of the signal itself. Both these things will be finite, they will work out in L2 and you will get good answers. Okay, so this is the way to define inner product and norm for two vectors. Okay, so here are a bunch of examples. This is very good practice. I'll urge you to do these examples carefully, and particularly the 4, 5, 6. Okay, so even 3, t par a, t par b, all of this is KL, and we're thinking of L2 from 0 to 1. Okay, so maybe one example I'll do, but all these examples are very nice. So for instance, if you want to do inner product here, it's all real sequences. You have to multiply and then you have to sum the series, right? So you have to remember your math 1 series summation. The first case will correspond to a geometric series. The second case will actually not be a geometric series, but you can use partial fraction sort of ideas to do the summation here. Maybe you know how to do it. It's not so important. But 1 and 2 I won't highlight too much. Just try it out. It's just for sequence spaces. In our course, we are not emphasizing sequence spaces. But 3, 4, 5, 6 you should do. You should have some comfort in doing it. Maybe I'll show you just for completion 3 and maybe 6, right? So I'll do that. Let me show you 3. So 3 is the inner product between t power a and t power b in the interval 0, 1. So what is the inner product? It's just integral 0 to 1 t power a. This is all real valued, right? So it's just t power b dt. That's it. So integral 0 to 1 t power a plus b, and this we know how to do, right? So it's t power a plus b plus 1 divided by a plus b plus 1, and the limits are from 0 to 1. So that is just 1 by a plus b plus 1. So that's the inner product. It's as easy as that. Okay. So you can just substitute very easily and you'll get to the answer. Okay. So the last question is about e power j 2 pi, did I get that right? 2 pi kt and e power j 2 pi lt in the interval 0, 1. Okay. So this is all, it's got complex and also you may be a little bit confused by it. So let me just show you how to do this. So it's going to be integral 0 to 1 e power j 2 pi kt times e power minus j 2 pi lt. How did I get the minus j here? Remember k and l are supposed to be integers. So we'll keep them as such. How did I get the minus here? Because the y of t needs the conjugation, right? So this times dt. So you'll have to do this. So, this will actually become 0 to 1. So, it is e power j 2 pi k minus L, right. So, it is cos 2 pi k minus L t plus j, right, sin 2 pi k minus L t dt. So, this is the integration. So, what you have to do is just split it into the real part and the imaginary part and do both separately. So, there is no problem here, it is just a function of one real variable. So, there is no real issue here. So, you can just do this plus j integral 0 to 1 sin 2 pi k minus L t dt. Okay, so, now these integrations are important to understand. See, sin and cos, they go through the entire cycle from 0 to 1, right. So, it is 2 pi k minus L, okay. So, these are all like full cycle integrals. So, what happens to the full cycle integral of sine? So, if you do a sine, if you integrate over the full cycle, you will get 0. Likewise, cos also you will get 0. So, sine and cos integrals are quite easy, but the only thing you have to watch out for is k being equal to L. So, if k is equal to L, what happens? If k is equal to L, this, so there are two cases here. So, let me just do this. So, one case is k is equal to L. So, if k is equal to L, cos will become 1, right. So, sine is anyway 0, so that will go off to 0. So, you will get 1 if k is equal to L, okay. That is easy to see. Now, if k is not equal to L, what is going to happen? You will get some number of cycles, right. So, you can also do it using formula and all that, it will work out correctly, but you can check that if k is equal to L, k is not equal to L, you will get 0, okay. So, because if this is an integer, from 0 to 1, when cos the angle goes from 0 to 2 pi some integer, okay. So, you will get a whole number of cycles in the integral, and when you integrate over integer number of cycles in a sine wave or cos wave, it will go off to 0, right. So, you can check that. You can also substitute using one of the formulae that you know, and you will get 0, okay. For integral cos and sine, you know the formulae, right. So, you have to use a function rule and all here, but you will get 0, okay. So, notice how interesting results are coming out, right. So, these two functions e power j 2 pi kt and e power j 2 pi lt are actually orthogonal, as in they give you the 0 inner product when k is not equal to L. So, notice this very interesting result. Kt is perpendicular to e power j 2 pi Lt in L201 under this inner product, okay, if k is not equal to L. It's very nice, isn't it? So, all these kind of orthogonality notions you can do very carefully here. So, I'll urge you to do these other functions also for different k, L, and use this kind of understanding. So, notice what we are able to do now with signals, we are able to associate angles, you know. So, there are two signals which are orthogonal now, okay, and that is very, very powerful to use in system design, okay. Thank you very much.